Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figure Outable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor students to think and reason like mathematicians. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be. Hey, Kim.
Hi.
Hey.
So I've been hanging on to this particular comment for quite a while because we knew that it would be kind of a fun topic to talk about.
Yeah.
But it would take a minute. So we're going to start today with me sharing what the comment was. So we got this message in one of our groups. I can't remember, probably the teacher Facebook group, where Kim said, okay, I have officially listened to almost all of the episodes. I wonder if she's kept up since then. And she said the amount of times that I've been like, oh, crud, I should have taught that. Yikes. She said, I've been enjoying them so much. And being that my name is Kim, also, sometimes I'm listening. And when you say Kim's name, I have to stop myself from answering. Thank you. She said, now that I've been listening, I'm fairly certain that these questions are not answered in your episodes. So she's keeping track. So here's a couple of questions. She said, 1, what is the figure-outableness? Is that a word? Figure-outableness?
Works for me.
Of PEMDAS. And then she also said, what's your thought process when you want to write a problem string? So 2 different questions. And then she says, thanks for all that you and Kim do. It's made a huge difference in how I'm approaching planning for my 3rd grade class. So that's super fun. So, Hey, Kim.
So the Kims of the world are super thoughtful and they take good notes. They take good notes and good attention to detail. Nice.
That's right. Yeah. So Kim, we sure wish that you were in Journey because we do work there with writing problem strings. So it's a big topic, but maybe that'll be fun to us to do in an episode, and we'd have to dial that back because it's a lot of thinking that goes into it. But in the meantime, we are going to tackle your question about PEMDAS today. So many people have asked the same thing.
Yeah. So PEMDAS. But love the fact, Kim, that thank you for your comments and your suggestions and wonders. Love the fact your name is Kim. And thanks for listening, Kim. Yeah. Kim, pick a Kim, any Kim. I don't think I've ever met a Kim I don't like. Several Kims several Kims in my life that I like. Yeah. And I do every once in a while remember the way Robin, our friend, says your name. Kim.
Yes.
Many rules.
Yeah.
So PEMDAS, and some people are like, what does that even mean? And it's kind of funny because my husband was looking over my shoulder and he read, please excuse my dear Aunt Sally. And he was like, what is that? Mm-hmm. That's a way of remembering PEMDAS. Mm-hmm. And in fact, I didn't, as a student, ever hear PEMDAS. I only heard, please excuse my dear Aunt Sally. So if you say the letters of those names, please excuse my dear Aunt Sally, that is PEMDAS, PEMDAS. Yeah.
Well, that's what you and I grew up with, maybe.
Yeah.
But there are some, people would call them improvements, maybe, but other acronyms. Our Canadian friends probably use GEMDAS. That's another popular one. Mm-hmm. And in the UK, I just recently learned there are BODMAS and BIDMAS, like all these acronyms that we're trying to make sense of.
And these are all good faith attempts to help students memorize and spit stuff out for order of operations.
Yeah.
And let's just upfront admit order of operations for many students appears to be completely random and nonsensical and difficult, and
Mhm.
teachers feel
Mhm.
that. And so there's this good faith effort to go, okay, I know this is hard. Let me make it easy for you. I'm going to come up with these initials that stand for this stuff, and then you're
Yeah.
going to use that to help you solve these problems. Here it is. I'm going to clearly tell you, show you. Now you mimic,
Yeah.
which,
And
go
go ahead.
ahead, is a fine thing to do if math is fake math.
Yeah.
If math is a thing to rote memorize and mimic, then by all means, let's help students rote memorize and
Yep.
mimic it well and correctly and easily, and not make them guess, not make them, guess what's in my head. Let's just tell them what it is clearly and give them things to practice, and bam, they could be successful at that mimicking.
Yeah. Yeah.
What if it's not? What were you going to say?
Yeah, I was going to say before we move into the episode too far,
Mm,
let's just ask people, just to think about for a second, like, what did order of operations make sense to you when you were growing up, or does it make sense to you now?
hmm
And how did you think about it? Why did it make sense if it made sense, or maybe why didn't it if it didn't make sense?
Yeah, we're super curious. We'd love to
Yeah,
hear from you on pick a social media platform and just let us know. Like,
yeah,
when you were a student, did you understand order of
yeah,
operations? Did
yeah,
PEMDAS make sense? Was math fake to you? And so you were super glad when a teacher gave you BIDMOS or
yeah,
GEMDOS or, like just do this. And you were like, I'm going to do that. Good.
yeah.
I'm done with my homework, moving on to real stuff.
Well, and I'm also
Um,
curious about if that's something that you say. Do you hold PIMDAS in your head now, or do you think and reason about operations now? That's interesting.
yeah. Yeah. What do you do? Yeah.
So we have all probably seen social media posts, right? Where pick any social media, where these crazy memes about which answer do you think, and so typically there's going to be some equation uh, or expression actually, and it'll say, which answer do you think? Is it 1 or is it 9? And then there's this slew of comments where people are arguing back and forth about which one it is. I actually just looked not too long ago, and there was one there. And one of the comments was that somebody said the order of operations was invented in 1912, and people were screaming at each other. And he was like, are you serious? We're still talking about this? But another comment was really fantastic. And they said, this was made to confuse people. Any sane person who wanted to express this wouldn't write it this way, which I thought was really interesting, that somebody was calling out the confusing nature of some of these posts that people are going back and forth arguing about.
Yeah, and so I think this particular one was written
Yeah.
6 divided by 2,
Hmm.
parentheses 1 plus 2.
Yeah.
And if you just like 6 divided by 2, parentheses 1 plus 2,
Yep.
this person's point was, you've written it that way to confuse people. Any
Yeah.
sane person who wanted to express that thing wouldn't write it that way.
Yeah.
They would be more clear in the way they write it.
Right.
And that is the point of the work that we do with order of operations or
Yep.
PEMDAS or pick your thing.
Yep.
Now, wait a minute. What does that mean? The point is communication.
Hmm.
The point is that we want to get something done. We want to have a particular outcome given some inputs, and we want to have there not be confusion in what we want done, how. And
Yeah.
so we had to figure out ways of communicating. Order of operations. Would you consider that order of operations is all about communication?
Hmm.
Now, that's maybe I'll say that this order of operations is tricky because, like many parts of mathematics, it's twofold. There are bits of order of operations that are social convention, and there are bits of order of operations that are logical mathematical. Because there's this mix of two different types of knowledge that are imbued in what's happening, that can get mixed up and messed up, and it can appear to be all social, all convention. And we've talked long and hard in other episodes on the podcast about the difference between social knowledge and logical mathematical knowledge. If something is social knowledge, you have to just tell people. If we've decided by convention something is true, then you have to tell people there's no way they can figure it out on their own by reasoning because somebody chose it to be that way. Like we just
Right.
defined it by convention to be that way. But if something is logical mathematical, telling someone is most of the time not enough. They actually have to deal with the relationships and get their brains to think in that way, and then they own it enough to actually do something with it. And so order of operations is not cut and dry
Right.
because it has that mix. So a big question that I think we could all consider as we are trying to teach order, if you are a teacher who teaches order of operations, if you could have in your mind that the emphasis, the big overarching question is, how will you know what I mean? Well, we're going to have to understand each other's language in order to know what we mean by that. I'll tell you just a funny example. Some of you know, I played semi-professional basketball in Switzerland right out of high school. So right out of high school, I went to Switzerland. I played on this professional basketball team. I had a blast. I learned some Italian. I learned some German. We had some people from Yugoslavia when that was still a country on the team, and like all this crazy stuff going on. And one day, I was walking down the street. I think I was leaving practice or something, and I noticed across the street one of the gentlemen who was on there was a board that owned the team, and I saw him across the street, and I waved at this gentleman like, "Hey, hi," like I recognize you, and I waved. Well, I waved in such a way I didn't know. I found this out later. Means come here in in Italian. And so I'm like acknowledging, "Hey, I see you. I know who you are." And he looks at me and he goes, "Oh." And I could see like this look on his face was like, "Oh." And it was almost a little bit like, "Are you really telling me to come here?" Now, I didn't know that till later, right? But it was kind of this look like, "Oh, I'm being commanded to do something. Well, here I come." And he marched across this busy street and then he says like, "What do you need?" And I was like, hi." It was just, and
That's funny.
later I realized, so we weren't communicating.
Yeah.
In mathematics, we need to have a language that we can communicate what we mean. So,
Yeah.
if Kim, let's do an example. Ready?
Okay.
If I said to you, pick a number, and you can pick any number you want. Maybe pick a number that's kind of smallish. Like,
Okay.
don't be over 100. Okay, so pick a number.
Okay.
Add 8.
Okay.
Okay, now divide that by 2.
Okay.
Okay, now subtract 4,
Okay.
and then double all of that.
Double my final amount.
hmm
Okay.
Okay, what'd you get?
4.
Now, do I really care? But
No.
what if I wanted to give anybody a number and do those things? But hey, I actually got to go do some things. Will you do that while I'm gone? And I can't just tell you those things in order. I
Yeah.
actually need you to do those things that way. But I got to leave the room, and so I need you to do it.
Yeah.
How could I communicate to you that I want you to take a number and I want you to add 8 to it, then divide that by 2, then take all of that and subtract 4 from that, and then take all of that and multiply it by 2. And you might be interested to know that I'm actually looking at what I wrote on my paper, not what I had planned to have you. I'm not looking at the words I wrote initially. I'm looking at a way that I represented that mathematically.
Mhm.
And now that I've looked at 2 parentheses n plus 8 all divided by 2, subtract 4. So I've got the quantity of n plus 8, n's your number, n plus 8 divided by 2 minus 4, all times 2. Oh, now that's what I have written down as the instruction that I might leave
Mhm.
somebody to do to solve that problem.
Yeah, I like that you're calling it, communication and that it
Mm.
almost feels like an instruction.
Yeah.
We would all want to follow the same instruction in order to end up with the same thing at the end. If we're
Mhm.
building something, we need to follow the same instruction.
Mhm.
Um,
Mhm. And we need to be able to communicate. And if I
right.
say something that is unclear, if I'm like, "Oh, do this," well, in fact, at some point when I said, I think I said, pick a number, add 8, divide by 2.
Mhm.
You could have said, wait, divide the 8 by 2, or divide my number plus 8
Right.
divided by 2.
Right.
And so I would want to be specific about that. I would want to clearly communicate my intent for you to do those things. And once I've clearly communicated what I want you to do, well, then we could actually look at what I asked you to do. And there's a possibility we could simplify what you need to do.
Mhm.
So if anybody wrote down what I just said, 2 times the quantity, n plus 8 divided by 2, that subtract 4. In fact, maybe
Mhm.
I'll say it even a little bit differently. N plus 8, that divided by 2. Then take that quantity and subtract 4. Then take all of that and multiply that by 2. Well, if you do that, you notice that there's some 2's that I'm dividing by and multiplying by that I could divide out, and I could end up with a simplified your number plus 8 subtract 8. Well, your number plus 8 subtract 8 means it's just your number. So, Kim, you said you got 4. Did you start with 4?
Yeah.
Bam! So you could try this with any number. You could start with 3 and do all that stuff, or you could just know that you're going to end up with your number at the end because of the way I kind of set it up.
Yeah.
So you can actually simplify it if you understand mathematics and the properties that are involved, the relationships that are involved. That can be a useful thing. Let me actually just make a kind of historical note, if I may. So most of us have heard of Rene Descartes. Descartes was the guy who said, "I think, therefore I am." He was into philosophy. He was kind of a Renaissance man. He did a lot of different things. One of the things that he did was a lot of work in mathematics. And he was very prolific. He wrote a lot of things in mathematics. And because of that, people from around the world at that time were trying to read his proofs, his writings, his thoughts about mathematics. And so they needed to understand what he meant. And so they would ask him, "Hey, when you write it that way, what do you mean?" Because at that point, we didn't have a lot of social convention. We had different ways of representing doing different things. In fact, I'll just pop in that when calculus was invented in 2 different places, one in Great Britain and one in Germany, Leibniz and Newton were both, I just switched them, by the way, where they were both inventing calculus. The way they notated calculus was different. That
Mhm.
was interesting. Like they were using different notation because as they were inventing it, they were using each other's notation. We had to sort of get to a place where we began to use, or as a society began to use the same notation. It's about communicating your ideas. And so if we would consider that that is the main upshot, that the biggest reason to help students have a motivation to learn order of operations is not so that they can do, Kim, we've seen them, these worksheets of 15 operation
Oh,
long
yeah.
problems where it's almost like a test of stamina.
Mhm.
Like, can you make it through this like really complicated thing?
Right.
Um, is that really the point? The point is when I give you a mathematical expression that I intend for you to do in one way, that it means these things. Can you read that? Are we communicating? Do you understand what this notation means?
Right.
So again, there's sort of 2 parts to it. One is there's the part that is the social, how we have decided to write multiplication. And man alive, is anybody else out there with me? Raise your hand right now if the fact that we have so many different ways to write multiplication is a little nuts to you. For example, when you learn multiplication, don't we use that little X symbol? Like the time symbol is kind of a little X. It's kind of it's not really an X, it's a little tiny X that we use that. But boy, then when we get to kind of algebra, we don't typically use that anymore because now we have x's as variables. And so that gets confusing. We have the tiny x that's multiplication and the x that's a variable. So then we tend to use a dot that means multiplication. But don't forget that when we have all that stuff going on, we often put parentheses or even brackets to mean multiplication.
Right.
Like we
Right.
have all these different symbols to mean, and then we're on a computer. So now we use an asterisk, right?
Mhm.
And so all these different things, why is that? Well, y'all, because we developed different symbols at different times to suit the needs of the time. And as a society, we've kind of adopted all of them. And we haven't yet said as a society, no, let's not use that one. It's too confusing. And frankly, I don't know this for sure, but it's a bet on my part. I think the asterisk came into being because we needed to have an easy symbol using computers.
Readers, yeah, yeah.
Yeah, I don't think we ever used asterisks to mean multiplication before
Right.
keyboards, before we had to like type stuff. All right, so notation has this part of it that is social, that we just decided we're going to make these symbols to mean these things. But there's also this logical mathematical part of it. And Kim, when you and I were talking about doing this podcast, I believe it was you that said, "Well, wait a minute. Isn't it interesting I don't know if you want to talk about it, if you want me to talk about it. This idea of multiplicative and additive and how they're kind of related.
Oh, yeah, yeah.
Yeah.
So when kids are early learners, they move from learning addition or addition subtraction into learning multiplication and division. Addition subtraction comes first. But
Mhm.
with the
Mhm.
order of operations, we're asking them to think about multiplicative ideas and then think about additive ideas. So in other words, when we're talking about doing exponents, that is repeated multiplication.
Mhm.
And then we want them to do the kind of one step multiplication. But then after that, we say, okay, now handle the addition subtraction
Yeah, that's
because
sort of the
addition
PEMDAS of
subtraction.
it.
Yeah.
Yeah, the PEMDAS, right?
Yep.
Parentheses or and then
Hmm.
exponents, and then that's PE,
Yeah.
and then M is multiplication division. And that's
So I
sort of
think
go ahead.
I think maybe where we get it wrong sometimes is we want kids to think about grouping symbols or parentheses and exponents. But what we don't necessarily help them understand is that we're moving from the more sophisticated thinking to the less sophisticated thinking within an expression. So if kids understood multiplicative type things and then additive type things, we could help them understand why exponents first, and
Mm.
then why multiplication division next, and why addition subtraction at the end.
Yeah, and I'll back up even a little bit more. If the only thing we've ever done in addition subtraction is have kids mimic algorithms for addition
Right.
subtraction, we actually haven't built their additive reasoning. And
Sure.
then we go to multiplication and division, and if the only thing we've done is have kids mimic multiplication, well, first of all, rote memorize multiplication facts, and then mimic the long multiplication and division algorithms, and so we haven't built their multiplicative reasoning, then all of a sudden we dump them in these crazy things where these all the symbols on the page, and we say make sense of that. Oh, by the way, and here's PEMDAS, that'll help you.
Hmm.
Like, if they're not already reasoning multiplicatively and they see these numbers all crazy on the page, they're reasoning additively or multiplicatively, and they see all these crazy numbers on the page, like it's
Hmm.
just becomes, really, this is math fun. Can I go to recess now?
Hmm.
Like, and I don't think we can blame kids at that moment, because it literally then just looks like a bunch of gibberish that they're supposed to rote memorize. There are parts of it that we need to just tell kids, hey, this is what this multiplication symbol means. But that is not sufficient. That is the bare minimum. We have to build their reasoning, and we have to help them logically, mathematically get a feel for why we're even doing order of operation problems at all. And if I can just suggest, it's about communication.
Yeah. Well, and then you throw in this tricky part about if multiplication and division are both within multiplicative thinking, which one do I do first? The idea
Mm,
that multiplication problems can be done with the commutative property in mind, but division can't be. You get a completely different result. And then same with addition and subtraction. I can solve an addition problem, in either order because of the commutative property, but subtraction has to go in a certain way. So all of these big ideas of mathematics are at play at the same time.
yeah, yeah, nicely said. So today we thought we'd give you just a thing to think about, and we're going to talk more about PEMDAS. We're going to give you some suggestions of things to do. But here is a way that you could help students get this big idea of communication
Hmm.
in maybe less of a go plug and chug through 29 of these crazy problems, and
Yep.
more of a let's actually build some ideas and reasoning with a little bit of play involved as well.
Hmm.
So, big shout out to Robert Kaplinski, a colleague, a genuine good guy. We really enjoy Robert. He's done an amazing job moving math education forward.
Yeah.
One of the things, and only one, because Robert's done several good things, is his openmiddle.com site,
Yeah.
where he's created a bunch of open middle problems, and he has what's the word
Contributors.
about curate? Yeah,
Yeah.
he's curated a bunch of contributions from a lot of people around the world who have thrown in some open middle problems. And I'll throw out an example of an open middle problem that I think you could use to help build a lot of really nice things for students with order of operations.
Do
So,
you want to talk about what open middle
oh,
problems are first in general?
golly, will I do a good job of that? Would you do a better job?
I'll start and you can add on.
Okay.
So in open middle problems, there are each problem will say use these particular digits 1 through 9, 1 through 5, 0 through 7, whatever the prescribed digits are.
For that particular problem. Uh-huh.
And you will have an expression with some blank spots. And the idea is that you are to fill those blank spots with the digits that you're told to use in order to do something. Get the highest number, get the lowest number, get the closest to whatever. And so
Mhm.
you basically play with the digits that you're allowed to use to solve lots of problems in the goal of doing a particular outcome. So if the goal is get closest to 100, it's kind of like our, one of our favorite games is close to 100.
Mhm.
You have certain digits that you're rearranging so that you're often solving problems to get towards the closest 100. So he has a ton on his site of different expressions that you can use
For
to
different
reach
goals.
different goals. Yeah,
Yeah,
different
yeah.
standards, different
Different
goals that
big
you
ideas
can.
to build different big
Mhm.
ideas.
Mhm.
Yeah, yeah. It's a fine way to get kids kind of playing with an idea. And one of those is order of operations.
Yeah.
So here's a particular one for order of operations. There's others, but here's one where it says blank. So you're going to put a digit in this blank plus. Now we have parentheses, blank times blank. And I'll repeat this in a minute. So blank plus parentheses, blank times blank, and the parentheses.
Mhm.
So that quantity in parentheses is going to be raised to a power, but that power is a blank.
Mhm.
And then you're going to subtract something from all of that.
Yep. So you have 5 blanks total.
5 blanks total. You've got blank plus, that's the first blank. Then in parentheses, you have blank times blank. Those are 2 blanks.
Mhm.
Then you're raising it to a power that's a blank. And then you're going to subtract blank.
Mhm.
Okay. So if I may, I'm just going to, on my paper, I literally have blank plus parentheses, open parentheses, blank times blank, close parentheses, raised to the blank
Mhm.
minus blank.
Yep.
Okay. Now the instructions are use the numbers 1 through 5 to get the greatest amount for the entire expression.
Hmm.
So just to be clear, if you've never done this before, I could literally just put 1 in the first blank, 2 in the second blank, 3 in the third blank, 4 in the fourth blank, 5 in the fifth blank, and then I could figure out what I have and I could go, how high did I get? And then I could reverse those and put 5 in the first blank and 4 in the second blank. And I could then just figure it out. And so a student who really isn't thinking much at all or strategically at all could just throw numbers in there, figure out what it is, come out with an expression or
They
come out
can
with an answer.
tinker. In other words, they could tinker and
Well,
participate.
they could just not tinker and just throw things in and just get answers. Or
But
what we really want them to do is to tinker.
right, but
Yes.
what I'm saying is everybody could participate in that,
Ah,
even if they aren't thinking strategically.
gotcha.
So
Yes.
somebody who's
Yes.
messing and just kind of, oh, let me try this, solve. Let me try this, solve. Even if it's not strategic, it's something that your kids can access at all different ways that they're going to access it.
I guess to me, tinkering and messing means that you're being strategic. And I hear you saying, no, they're just like throwing them in there
You could
and
just,
seeing what they get.
so
Yeah.
maybe you're just plugging in numbers. Yeah.
Yeah. So let's talk about that kid who just throws numbers in there and then figures out the expression. Well, they're getting practice with order of operations. So as they do it, then you could be giving them feedback to go, yes, you've done that correctly. How high? So our goal here is to get the greatest amount. You could say, do you think that's the greatest amount you could get? And then you could walk away and come back. Or you could say, do you think you could get something bigger than that and walk away?
Yeah.
And so then kids can start to think strategically, or maybe they started from the beginning, but they could start to think, I've got
Wait,
the,
pause.
oh, sorry.
If our listeners,
I'm not going to give it away. I'm not going to
okay,
give it
but
away.
if they haven't had a
Oh,
chance to pause the podcast and tinker
you're right. You're right.
themselves,
You're right.
this is a good time to do that.
My bad. I was getting excited. So pause the podcast, use the digits 1 through 5,
Yep.
put them in those blanks and see if you can find the greatest amount. What are you thinking about? Then come back. All right. So come back. And now we're actually not going to give what we think is the answer for where the digits 1 through 5 could go in here. But I do want to raise some things that you could think about as you're as you're strategically deciding where to put numbers. Do you want to put the largest number somewhere? We're trying to get the largest amount. Where could you put the largest number that has the biggest impact? And if you're not sure, could you move that largest number around and see where it had the biggest impact? Where can you put the smallest number so that it will have the least impact? If we're trying to get the biggest outcome, maybe the smallest number we want to put somewhere so it doesn't really grow the outcome very much. Vice versa, if we wanted, what if the instruction was put the numbers 1 through 5 in there, so you wanted the smallest amount? Well, then
Mhm.
you can be asking that question. Does it land in one of those addition places? Does it land in one of those multiplication places? Does it land in
Mhm.
one of those subtraction places, or raised to the exponent place? Where does it make the most difference? And we'll let you play with that because it's kind of fun. And then you could tell us on social media where you think those numbers belong in there. We'll throw this out on my social media, and you can respond and tell what you're thinking about. Maybe even what you tried first before you found the
Yeah.
answer that you thought was the best.
Maybe like a week from now, we can put the highest amount that we got. Not put the answer, but
Just
can
the
you
result.
make it higher than this number?
Wow,
We'll
nice.
think about that.
Nice. I like it. I like it.
All right. So some major takeaways from today is that it's about communication, right? That's the point, is way to communicate mathematically what we're trying to accomplish. And there are both logical and social parts to what we're talking about with order of operations. So there's really some stuff to tell, which is the notation, but most of this is about development. It's really about multiplicative relationships and additive relationships. So there's some work to be done there. And multiplication is nested within exponents, and addition is nested within multiplication.
Big ideas that are happening. Y'all have some fun with order of operations. Thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.